In this example, we're asked to analyze a diesel cycle. We have a displacement volume for an internal combustion engine. It's 3 liters. The processes within each cylinder of the engine are modeled as an air standard diesel cycle with a cutoff ratio of 2.5. The state of the air at the beginning of compression is fixed, and we're given the pressure, temperature, and volume. We're asked to find the net work per cycle, the power developed by the engine if the cycle repeats 1,000 times per minute, so like 1,000 RPM, and 1,000 cycles per minute, and then the thermal efficiency of the cycle. So let's go ahead and sketch out a picture here. So what we have is a piston cylinder arrangement with some air in here. This is our system. It's a diesel cycle, so let me just let me draw a PV diagram. So state 1 is here. We're going to do isentropic compression from state 1 to state 2. So that's compression. It's compression because we're going from a large volume to a small volume, right? So that's an isentropic compression process. In a diesel cycle, from state 2 to state 3, that's where we're doing the combustion. And that's a constant pressure process. So that's at a constant pressure. So that's our combustion or heat addition process. From 3 to 4 is the power, the rest of the power stroke. There's actually some energy or some work being done from 2 to 3, right? If you look at the area under the curve, you can see, this is a PV diagram, so the area under the curve is your PDV work. So we're actually generating some work during that heat addition process. State 4 is at the end of that isentropic expansion. That's our power stroke. And there you can see that there's some additional work being done in this is the power stroke. So we're getting some additional work being done during that portion of the process. And then from 4 to 1 is the constant volume heat removal. So that's our diesel cycle on a PV diagram. So the first thing that we'll want to do is let's calculate the mass of air in the cylinder. Because we're going to find the work per cycle, we're going to need to find how much mass of air we have. We're given the information about state 1, so we can use the ideal gas law to figure out what the mass of air is. So from the ideal gas law, the mass is P1 V1 all over RT1. And we're given all this information. Just remember that R for air, 0.287 kilojoules per kilogram Kelvin. And we're given T1 is 22 degrees C, so we'll convert that to Kelvin. That'll be what, 295 Kelvin. And we're also told that the V1 is 3 liters, and you have to do a little unit conversion here. This will be 3 times 10 to the minus 3 cubic meters. So then you can, determine what the mass is from that. And when you do that, the mass comes out to be 3.5570 times 10 to the minus 3 kilograms. Okay. The next thing that we'll do is we'll determine the properties at the various states. Because when we try to find the net work in the cycle, we're going to have to use the first law. And the first law involves the internal energy, specific internal energy, and it'll also involve the specific enthalpy for a diesel cycle. So we're going to want to determine all of these values at the various states. So let's do that. State 1, we're told the pressure. We know the temperature. We know the volume. So we can use the ideal gas table for air. So we can go back to that ideal gas table, and you'll find that U1, the specific internal energy, is 210.5 kilojoules per kilogram. Another quantity that we'll make use of is the relative volume, and you'll see why we use that in just a moment. So we'll look that value up from the ideal gas table. That comes out to be 647.9. Okay, now let's move on to state 2. When you go back up to the problem statement, you see that the only real information that we have about state 2 is we know the I think we're given the displacement volume. Actually, I take this back. I had the wrong V1 now that I look at the problem statement again. V1 is given right here. So I apologize. V1 I had written down incorrectly. Let me fix that. That's 3.17 liters. So that's 3.17 times 10 to the minus 3 cubic meters. And then let me fix it down here as well. And okay, so that I just needed to fix. Okay, so what we know about getting to state 2 is that we know that the displacement volume is 3 liters. So remember that the displacement volume is the volume between the bottom dead center and the top dead center. So state 1 right here, that is at bottom dead center. Bottom dead center. That's where the volume is the largest. State 2 will be at top dead center. Right? That's where the volume is the smallest. So we're given that the displacement volume, which would be V1 minus V2, is 3 liters. That's why I got confused with 3 liters. So what that means then is V2 is going to be 3 liters minus V1. And, or do I have that the other? No, I'm sorry, I have that mixed up. It'll be V1 minus 3 liters. So that means V2 will be 0.17 liters, or 0.17 times 10 to the minus 3 cubic meters. Okay, so that's the volume at 2. That's one piece of information. The next thing is we'll make use of the relative volumes, that relative volume ratio. So let me write this down and then I'll explain it. Okay, so this is the relative volume. We can use relative volumes when you're dealing with an ideal gas and an isentropic process. Right, so if you go back up here from 1 to 2, this is isentropic compression of the air. Since the air is not an ideal gas and this is isentropic, we can make use of the relative volumes. So we can rearrange this to solve for the relative volume at T2. And we just calculated what V2 is. So V2 was the 0.17 liters. V1 we know is up here at 3.17 liters. The VR at T1, the relative volume at T1, we found from the table. So we can then calculate what the VR T2 is. That comes out to be 34.745. Then we can go to the ideal gas table to look up the corresponding temperature. And you have to do a little interpolation, but when you do, it comes out to be 896.15 Kelvin. And then to get the corresponding U2 value, the specific internal energy, that's 671.405 kilojoules per kilogram. And the specific enthalpy, which we'll make use of in a little bit, is 928.59 kilojoules per kilogram. All those come from the ideal gas table. While we're here, let me also calculate P2. So I want to find the pressure. Note that P2 and P3 are the same. That process from 2 to 3 is the heat addition, and that's a constant pressure process for a diesel cycle. So let me just calculate P2 while I'm here. So P2 from the ideal gas law will be mRT2 all over V2. We've previously calculated the mass. We know the gas constant. We just found the temperature. And the volume at 2 we calculated just a moment ago as well. Right, so we can plug those values in, and then what you'll get is P2 comes out to be 5,381.37 kilopascals. Well, we're going to make use of that in a little bit. So we've now found everything at state 2. Let's now go to state 3. To find state 3, we're going to make use of this cutoff ratio. We're told in the problem statement the cutoff ratio is 2.5. So what is the cutoff ratio? The cutoff ratio is the ratio of the volume at state 3 to the volume at state 2. It's the ratio of those volumes. It's basically how much of that volume as you go from top dead center to bottom dead center as the piston is moving downward. It's how much of that volume is involved in the combustion process. So that's called the cutoff ratio. So the cutoff ratio, RC, is the volume at 3 over the volume at 2. Okay, and that we're told in the problem statement that cutoff ratio is equal to 2.5. So we can then find V3, because we know the volume at 2, that's 0.425 liters, or 0.425 times 10 to the minus 3 cubic meters. And also, since the pressure is a constant, so P3 equals P2, remember that from 3 to 2, this is a constant pressure process. So the pressure remains constant. Of course, the mass is a constant because it's the same amount of air. You could show then that this ratio, the cutoff ratio, would also be equal to the ratio of temperatures. So let me just show that here using the ideal gas law. So if you use the ideal gas law, it would look like this. Right, from the ideal gas law, and then we know the masses are the same, R's are the same, pressures are the same, so this will be T3 over T2 as well. Right, so the cutoff ratio is that ratio. We already know T2 from up here, from the table lookup, so we can calculate T3. And when you plug in the numbers for that, T3 comes out to be 2240.4 Kelvin. Now that we know the temperature, we can go to the ideal gas table and find the corresponding U3 and H3. So if we do that, U3 comes out to be 1911.76 kilojoules per kilogram, and the H3 specific enthalpy is 2553.87. So again, we're just doing some property lookups. Let's also get the relative volume at T3 from the ideal gas table. We'll make use of that in a moment. That's 1.8925. So those come from the ideal gas table at that temperature T3 with a little interpolation. Okay, now let's move on to state 4, our last state. Okay, so what we know about state 4, as we know, first of all, the volume at state 4 is equal to the volume at state 1. Let's go back up to our picture. You can see that here. This is a constant volume heat removal process. So V1 and V4 are the same. So we know V1, that's given right here. It's 3.17 liters. Okay, so that's one piece of information we know. The other thing is we know that this is a in going from 3 to 4, that is a constant entropy process. So again, we're dealing with air, which is an ideal gas, undergoing a constant entropy expansion. This is the power stroke, and that's assumed to be constant entropy. So for a constant entropy process involving an ideal gas, we can make use of the relative volumes again. So VR at T4 over VR at T3 is the volume at 4 over the volume at 3. And so we can rearrange that to find the relative volume at state 4. All right, so this relative volume at T3 we just looked up in the table moments ago. V4 I just said was the same as V1, so we know that value. V3 we evaluated right up here from the cutoff ratio and the volume at 2. So we know all the information on the right hand side, so we can then solve for VR at T4. When you plug in the numbers for that, it comes out to be 14.1157. From there we can use the ideal gas table to look up the corresponding temperature. That's 1209.8 Kelvin. And again, we can look up the specific internal energy just like we did before. That's 942.17 kilojoules per kilogram. Little interpolation is involved there. All right, so now we have state information, which we'll use to determine the work and heat transfers involved in this cycle. Remember that in the problem statement, what we're trying to do is find the net work per cycle. We can do that a couple of different ways. I'll show you both methods. One way to do it is to calculate the work in going from 1 to 2. Right? So here work is being done on the air because we're compressing the air. This is a big volume to a small volume, so we're compressing the air. So work is being done on the air. From 2 to 3, that's work being done by the air because we're expanding. That's a constant pressure process from 2 to 3. And then there's work from 3 to 4 during the power stroke. So, and then from 4 to 1, there is no work because that's a constant volume process. So let's try to find the net work by calculating all of those individual works and then summing them together. So the net work out will be the work out from 1 to 2 plus the work out from 2 to 3 plus the work out from 3 to 4. And as I mentioned already, the work out from 4 to 1 is 0 because it's a constant volume. Okay, so to find these work values, what we'll do is we'll do the first law applied to the air for each one of those processes. So from 1 to 2, what it'll look like when you write out the first law, it'll look like the following. So for the work out from 1 to 2, what I'm doing is I'm applying the first law to the air. Changes in kinetic and potential energy are negligible, so we only have changes in the internal energy. From 1 to 2, that's an adiabatic process, so there is no heat transfer on the right-hand side. And then here's, of course, our work term. We just looked up values for the specific internal energies. We already calculated the mass of the air, so we can solve for the work out from 1 to 2. And when you plug those numbers in, that comes out to be minus 1.6394 kilojoules. Let me do the same thing for 3 to 4 now. So that'll look much the same. Adiabatic process from 3 to 4, neglecting kinetic and potential energy changes. So we can solve for that one. That one comes out to be, let's see, what does that come out to be? That one's 3.449 kilojoules. Notice that the work out from 1 to 2 is negative, that's because we're doing work on the air. We're compressing it. 3 to 4, it's an expansion process, so the air is doing work on the surroundings. Now let me address what's happening from 2 to 3. Go back up to our picture. Remember, this is a PV diagram. To find the work from 2 to 3, what I'm going to do is just integrate the yellow area under the curve here. If I use the first law, the problem is I've got a heat transfer. Remember that there's heat transfer coming in 2 to 3 here. There's heat transfer going out from 4 to 1. So, if I did the first law from 2 to 3, I'd have to account for both the heat transfer and the work. I don't know the heat transfer off the top of my head. I haven't evaluated it. I don't have any information. So another way for me to find the work is just to integrate under the PV curve, right? And this is a constant pressure process, so that's a pretty easy integration. It's just going to be the pressure at 2 multiplied by the difference in V3 minus V2. This is why I calculated the pressure here, is because I knew I was going to have to use it. So from 2 to 3, I'm just going to calculate as just P dV work. It's just P dV work. And I've already found what P2 was. I know V3, I know V2. I can plug those numbers in. And what you'll get is that comes out to be 1.3722 kilojoules. That's positive again because the air is doing work on the surroundings. It's part of the expansion. If you take all of these values, sum them together to get the net work out, you'll get that the net work out is 3.18 kilojoules. This is the work over the cycle. Now there's a different way we could find this net work out, and that is we could apply the first law over the whole cycle. Okay, if you apply the first law to the air over the whole cycle, the change in the internal energy will be 0 because it's a property, and the property doesn't change over the cycle. So on the left-hand side of the first law, it'll be 0. On the right-hand side, you'll have the heat transfers coming in. So this will be coming in from 2 to 3. And then we'll have the heat transfer out from 4 to 1. And then we'll also have the net work out over the whole cycle. So to find that net work out, of course that'll be Q in from 2 to 3 minus Q out from 4 to 1. So then you'd have to find the heat transfers in each of those processes. Okay, so let's do the easy one first. Let's do the Q out 4 to 1. Okay. Now if you go back up to our picture, our PV plot, you can see that from 4 to 1, that's a constant volume process. So there is no work being done from 4 to 1. It's only heat transfer. So when we apply the first law there, on the left-hand side, it'll be the mass times U1 minus U4 equals minus Q out 4 to 1. And then again, there's no work because it's a constant volume process. So we can solve them for Q out. When you work out those numbers, that comes out to be 2.6025 kilojoules. Now let's find Q in 2 to 3. That one's a little more complicated. When we apply the first law to that, we'll have, on the left-hand side, we'll have mass times U3 minus U2. On the right-hand side, we'll have Q in from 2 to 3. And there is work being done, right? So if you look up here from 2 to 3, there is certainly P dV work. That's the yellow volume there, or the yellow area. So we have to include that. That's P dV work. So we could just make use of this value up here, or I'll just write it in terms of the PDV work again here. So this will be minus P2 times V3 minus V2. Okay. Now we can rearrange things here to solve for Q in 2 to 3. So let me just combine some things together. This will be U3 plus P2. Remember that P2 and P3 are the same, so I'm going to just write it as P3 times the specific volume at 3. It'll look like that. So what I've done in writing that equation is instead of volume here, I'm using specific volume. So that means I have to pull out a mass. So that's why the mass is here with square brackets. And then just remember that P3 and P2 are the same because it's a constant pressure process. If you look at that for a moment, those are just specific enthalpies, right? These are specific enthalpies here. So that's why I looked up specific enthalpies in the property table. So we know those values. We can plug them in. And when you do that, Q2 to 3 comes out to be 5.7811 kilojoules. So now we know our Q out and our Q in. We can plug those back into our expression up here for the net workout, and you get the exact same value. It also comes out to be 3.18 kilojoules. So the same value as before. I just wanted to show that you could do it two different ways, whatever is your preference. All right, so that's part A of this problem, find the net work per cycle. Now part B is to find the power developed by the engine if the cycle repeats 1,000 times per minute. So this is just asking us to find the power. So the rate at which we're doing work, so out net, will just be the work that we're doing out per cycle. So this is per cycle, right? So we know that value. That was what we just calculated. That's the 3.18 kilojoules per cycle, right? And then we're told that we have a cycle that we're doing this. The engine is operating so that we're doing 1,000 of these cycles per minute, per 1 minute. And of course, we know 1 minute is 60 seconds, right? So we can calculate these together. So the 3.18 times 1,000 divided by 60. And if you look at this, the units, the minutes will cancel out, the cycles will cancel out. And what you're left with when you plug in the numbers is this will be 53.0 kilojoules per second. And a kilojoule per second is also known as a kilowatt. So the power generated by this diesel cycle is equal to 53 kilowatts, because that depends on how fast the cycle is being executed. All right, so that's part B of the problem. I'll go back up to the problem statement. So we've just done part B, and now part C is to find the thermal efficiency of the cycle. This one's pretty straightforward. Hopefully there are no surprises here for you. The thermal efficiency will be the net work out divided by the heat coming in. Not the net heat in, but just the heat in. So the net work out we just calculated is 3.18 kilojoules. The heat coming in is this heat from 2 to 3. So that's going to be, I'll just write it as Q in 2 to 3, which is the 5.7811 kilojoules. So when you plug in those numbers, that comes out to be 0.550. or 55%. All right, so that's everything in this example. Just a few things to kind of recap what we've done. First thing that we did was just draw a system and then sketch out what our cycle looks like. Here I chose a PV plot because I really wanted to emphasize the PDV work. We used the ideal gas law a couple times in the problem. One of the first things that we did was we found the states. We found all the properties at the various states. And the way we did that is we used the ideal gas table, because we're dealing with air. To connect information between the states, we made use of the displacement volume, and we used the relative volumes because we knew we were dealing with an ideal gas undergoing an isentropic process for a couple of those processes. We also made use of the cutoff ratio. That's just a definition specific to the diesel cycle, so you have to go back to your notes to look at what that definition means. So we made use of that. Here's the relative volume again during the isentropic expansion. And then once we had all that state information, what we did is we applied the first law multiple times. You could have done this a couple of different ways. You can find the work individually for each process. And then we also, for the diesel cycle, we did some PDV work, and we summed that up to get the net work out. Another way you could do it is to do the first law over the whole cycle, and then calculate the heats that have been added or removed during different portions of the cycle using the first law. Okay, and you have to be a little careful in going the combustion process for a diesel cycle. That heat coming in, when you apply the first law from 2 to 3 during the combustion process, you have to keep in mind there's a little bit of pressure work that's being done there. And then lastly, we found the thermal efficiency just using our normal method. It's the net work out divided by the heat that we put in. So that's standard. That's a standard definition for thermal efficiency. All right, we'll go ahead and end it there.